Hello, everyone. My name is Daria, and I'm a head research scientist at Cerebras. Today, I would like to introduce to you the innovations that happened in mixture of experts field. In particular, we're going to look at Qwen3 model innovations and compare it to one other popular model called DeepSeq v3. I kind of wanted to give you an evolution of what happened in the LLM space. We started with GPT-3 models a few years ago. The model there was 175 billion in total size. What we showed that as you increase the model in size, you actually unlock more capabilities and improve the quality. After that, we realized that we also need to scale the data, improve the data, curate the data, deduplicate it, and really improve the generalizability of our data sets and our models. As the result, we released the Llama 3 series of models. Llama 3 is 400 billion in size. So you can compare it to GPT-3, which was only 175 billion. So we're growing the model size still. Finally, most recent release called DeepSeq v3, that model was even bigger. So it was 600 billion in total parameter count. And what they demonstrated is as you increase the model size, you need to become smarter about how you create how you change the architecture in a way that it becomes more compute efficient. So what they showed is that you can train a model of 600 billion size with the compute needed for 400 billion only. How did they do it? DeepSeq v3 has a mixture of experts architecture. Mixture of experts essentially allows you to have a set of specialized networks within one network, and you only activate a portion of them as you move the tokens through the network or the words through the network. That essentially allows you to kind of separate compute from the model size. You can continue improving the model size without increasing the compute. As the result, DeepSeq v3 was the state-of-the-art model. It improved the quality, not just to compare to the closed open source models, but also closed source models such as GPT-4o and Claude 3.5. One interesting benchmark that I would like to emphasize here is called GPQA Diamond. That one is specifically created for questions of the PhD level. Type of questions where only people with a specific degree can answer them. So you can see that the human level quality is about 65%, and DeepSeq v3 is really close to that. Now, how does it actually work? Why mixture of experts is so efficient, and what's the motivation to have it in the architecture? If you look at the transformer network, there is a set of different layers. On the right, you can see the transformer decoder block. They're more than just embedding, attention, and feed-forward layers, but as a nutshell, these are three types of layers. They all have different tasks. And if you look at the feed-forward layer task in particular, its task is very complicated. You have to sort of disentangle all the information that comes from the previous layers. It can be information from different languages. It can be information from different domains. Like let's say math and biology, and feed-forward network has to train one set of weights that is good for solving different type of tasks. Usually it's a really hard task, and what we would want is to simplify the task for feed-forward network. This is exactly what mixture of experts is solving. Instead of having one set of feed-forward networks, we're going to introduce a list of or a set of feed-forward networks, and each one we're going to call expert. In addition to that, we're going to introduce a network called the router, and that router network's job is to basically decide which expert is the best suited to process a particular word that we route through the network. Now, as we separated experts, we also improved the generalizability of the whole architecture, because now each expert has to focus only at the particular portion of the task and doesn't have to create weights that are good for solving different type of questions. Now, with all being said, DeepSeq v3 trained the mixture of experts architecture. They did different techniques. They introduced different techniques to make sure that you have decent load balancing, which means that we don't want to introduce idle experts that kind of like stay without any tokens and not process any information. So they introduced the concept of shared experts, which essentially are generalist experts in your network. And those are never specialized. So you can think about it as with shared experts, you sort of semi into mixture of experts world and partially into the monolithic world. That's done essentially to improve the load balancing of the network, mostly for that. As the result of it, we can see that here I have the heat maps of different experts. We compare experts to the other set of experts in a given layer. As you see, the diagonal elements here are basically experts compared to itself. So they are the brightest color, yellow. Everything close to yellow means that there is a lot of overlap. As you can see here, in the first 26 layers in the DeepSeq v3, there is a lot of overlap between different experts, which means that we are introducing enormous redundancy in the network this way. And one of the reasons is because we have shared experts. Now, one of the most recent releases of mixture of expert models also noticed that problem and introduced a technique to load balance the load between different experts and also improve the specialization. So we don't have that much redundancy in a network. In a nutshell, most of the implementations uses a microbatch to calculate the load balancing loss or any load balancing technique that you use. And in the microbatch in pre-training, we just have a handful number of sequences that we try to load balance across versus having the global batch, which usually has much more. Because of that, what you're trying to do is within a sequence, you're trying to load balance the tokens to move them to all experts in a given layer. And it's usually really hard because within the sequence, you have very similar words. So it doesn't really make sense to separate them into the experts. But because you regularize hard to make sure that there is load balance, you start losing on specialization. Experts are confused what they have to specialize in. The modification that Qwen3 proposed is to change the way that we aggregate the load balancing loss. Instead of doing the micro batch size aggregation, let's do the global batch size aggregation. And there is an algorithm that they proposed to make it more efficient compared to just the brute force version. As the result, you can see on the left, they have an improvement in terms of the quality. So the network became more generalized. At the same time, there is improvement in specialization. They started noticing that some experts are actually more specialized in particular tasks like math, coding, etc. Here, I kind of also wanted to show you the impact. As you improve specialization, you improve the quality of your model compared to all other models that didn't have that trick. So you can see that Qwen3 model, despite being, it is beating Llama for Maverick, despite being 2x smaller in total parameter count. And it's beating DeepSeq v3 as well, despite being 3x smaller than their model with total parameter count. This kind of shows you the level of redundancy that previous models have and how Qwen3 is trying to address the problem with redundancy and improve specialization of the network. This kind of want to close that as you increase the model in size, it's important to treat expert not just as the computational chunks, but also as specialized networks. And I believe as we continue increasing the expert size, expert count, and increasing the model size, it's really important to understand how do we scale them, whether we introduce redundancy, and how to attack redundancy with a better specialization. Thank you.